Hello everyone, welcome to another video of quantum field theory. In today's video, we'll be finishing our last video on the Maxwell equations. So a brief recap here. We derived this equation for the electromagnetic vector potential, and that is the solution to the Maxwell equations. We can then plug in this potential into the Faraday tensor to get the formula for the electric and the magnetic fields that solve the Maxwell equations. And if we were to plot this field onto space, we get something that looks like a plane wave, but formed by vectors instead of scalars. And if we were to put the solution into this continuity equation over here, we find that the first component of the vector potential must equal the last component of the vector potential. I didn't go through these steps here since I went through them on my second video on the Procca equation. It's the exact same steps, but for a massless gauge field, so I'm pretty sure that it would be easy to follow if you just watched the second video on the Procca equation. So by using this equation, and by letting our momenta only move in the z direction like last time, we find that we can use these three polarization vectors as a basis for our polarization space. So this is a unit polarization vector in the x direction. This is a unit polarization vector in the y direction. And this is a unit polarization vector in neither the x or the y directions, since it has this time component over here. So this is going to be what's called a longitudinal polarization vector. So there is a problem that we can see by studying this third basis vector. So we can see that this vector is not orthonormal. Because if you take the dot product of E3 with itself, we get 1 squared plus 1 squared, which just equals 2. And so this does not equal 1. So E3 is not normalized. E1 and E2 are normalized, but 3 is not. And E3 is also, well, it is orthogonal to the other vectors, but it's not orthonormal to the other vectors since it's not normalized. So this already tells us that this E3 vector is going to cause some problems since it is not orthonormal. When we had a mass gauge field, there was no problem since we didn't have this very strong constraint where E0 had to equal E3. But the fact that our field is massless implies that the first entry of the vector has to be equal to the last entry, which means that E3 just can't be normalized. So it turns out that if we take this idea further, we can find out that massless gauge fields only have two non-trivial, linearly independent basis vectors instead of 3, like a mass gauge field. We can understand this by using the gauge transformation again. So a brief review, we can transform some vector potential, or gauge potential, into some new gauge potential, which equals the old one plus what's called a gauge. This is called a gauge. And this gauge transformation leaves the Maxwell-Lagrange unit invariant. This is called a gauge invariance or a gauge symmetry. And it turns out that gauge symmetries have some very big impacts in physics. this is again using Noether's theorem, which I talked about on my 2 videos titled Noether's theorem. But essentially, gauge symmetries, they yield conserved quantities and other cool things. But in our cases, using a new gauge can help simplify lots of equations. In fact, by using a new gauge, we can find out that any third polarization vector that we choose actually will yield the zero vector. And I'm going to elaborate on that right now. So we can choose a gauge. Let's choose a gauge F. Yeah. Oops. What did I just do? Okay, so our gauge X mu, F of X mu, let's choose it where F of X mu equals I over KZ e to the I K mu X mu. Oops, my pen just died. Let me just charge it for a moment. So all we're doing here is we're choosing some gauge. We're allowed to choose any gauge we want. We're choosing a gauge where F of X mu, which is a field in space-time, equals I over KZ times e to the I K mu X mu. Alright? And this means that our gauge transformation becomes this plus the derivative of I over KZ e to the I K mu X mu. Also, we should technically use K3 to be consistent with our notation. But it will be the momentum in the Z direction. So all we have to do now, you just take this derivative. It's not very hard to do. I over K3 times I K mu e to the I K mu X mu. These i's give us a negative sign. So you're going to have minus K mu over K3 e to the I K mu X mu. Now, an important thing to note. Wait, actually, let me think for a second here. Yeah, so an important thing to note is that our 4 vector, our 4 momentum, only has values for kz. Oh, let me just write it out real quick. I don't like this notation, but like I've said this many times. I don't like it when people call k mu a vector, since it's not really a vector, right? But we would expand k mu in terms of vector components. So that's going to be k. So we say this is k mu. So this is going to be k3, not k3. E to the I K mu X mu. And now we have this relation over here. We can then plug in our already known value for A naught. And we would get E to the I K mu X mu times E rho. Now we chose the third E rho value to be this. So let's just plug that in. Let's plug that in. 1, 0, 0, 1. This is our third polarization vector that we chose. We have this minus, it's going to be K3 over K3, 0, 0, K3 over K3, e to the I K mu X mu. So this is going to be equal to 1, 0, 0, 1, e to the I K mu X mu, minus, so this is just going to be 1, since it's the same thing divided by the same thing. This is also going to be 1. So we have 1, 0, 0, 1, e to the I K mu X mu. And we can just factor out the plane wave. And we get not the zero vector. Sorry, we don't get 0. We get the 0 vector. Since this minus this, is the 0 vector. And then the 0 vector times anything is also the 0 vector. So here's our answer. So this may seem totally, what's the word? Totally incongruous to the current conversation, but it's very relevant. Since we just found out that by using the third polarization vector, we are able to choose a gauge such that our new vector equals 0 if we use the third polarization vector. So to summarize, if we use the E3 polarization vector, we are able to choose a gauge transformation, I should say, such that a rho equals a 0 vector. Alright, because here's a rho. Here's like the new a rho. So it's not like our old field is a 0 vector, but our new field is a 0 vector. So I should say a rho tilde is a 0 vector. And since gauges don't really change anything about the dynamics of our system, this means that by using E3, we don't really get any interesting results, since we can always change our gauge to make a rho tilde equal the 0 vector. So yes, it's not so I'm trying to think of how to phrase this. So we do have 3 basis vectors, but for the third one, we can always make it such that our new field is the 0 vector. And this tells us that photons, or massless gauge particles, or massless gauge fields, only have 2 non-trivial, linearly independent basis vectors instead of 3. Because if we use that third one, we get the 0 vector for our new for our new vector potential, right? But if we do the same method for these two guys, we don't get the 0 vector. And since the 0 vector is trivial, and these are non-trivial, we say that photons have only 2 non-trivial polarization vectors. Technically, it kind of does still have that third, but again, we can always choose a gauge such that it's 2, which is why I say non-trivial polarization vectors. No matter what you do, you cannot choose a gauge such that these two become the 0 vector. It's not possible. So here you might see some flaws in my argument. First of all, we only chose the momentum vector to move only in the z direction, right? And we only let it move in the z direction, and then we chose that the E3 vector was 1, 0, 0, 1, right? So what if we don't want our field to only move in the z direction? What if we don't want the third vector to be 1, 0, 0, 1? Does our argument still hold? It turns out that it does, because it doesn't matter what we choose the vector to. It doesn't matter what momentum we choose. It doesn't matter what third basis vector we use. We can always still find a gauge where the EM potential will be 0. I'm sure that there's some general proof for this. I do not know the general proof for that, but you can kind of see if you just test different cases, and hopefully that will convince you. So yeah, in short, the EM field has, for massless particles, for massless gauge field, it has only 2 linearly independent solutions. So here's the solution. And I talked about the solution in the last video, in the last video of the Procca equation. So it's pretty similar. Here we use R instead of rho, just because it's standard in textbooks to use R instead when writing the general solution. And here mu is used to differentiate the actual vector from the components. The components would actually be the. Wait, no, never mind. Yeah, the components would actually be like E naught, E1, E2, and E3 that are components of some E vector. Probably could have explained that better, but. And then we have the superposition over plane waves, and then we have a sum over our polarization vectors. And we have r equals 1 to r equals 2, since we have only two non-trivial, linearly independent polarization vectors. And that is the general solution for the Maxwell equations. Under the Lorentz gauge, we can have totally different solutions if we choose totally different gauges, by the way. You don't have to stick to one gauge. I don't want to make you guys leave this video thinking that, oh, this is the solution. No other solution can exist. This is the only one. I'm not saying that. I'm just saying that we can just choose some gauge such that this is the solution. So yeah, those are the Maxwell equations and the solution. In my next video, it's gonna be the second to last video of the series. This series is actually almost done. Don't worry, I will make a chapter 2 to QFT where we'll cover second quantization. But chapter 1 just focuses on understanding classical fields and getting a good grasp on classical fields. So with all that said, thanks for watching, and see you guys maybe tomorrow, sometime soon. Bye.